So our third talk is about SRC, Scalable Reliable Connection for RDMA. And our speaker is going to be Yiren Zhao. So Yiren is now a master's student at University of Toronto. She's interested in building efficient network systems for cloud and AI infrastructure. And her work focuses on networking for distributed machine learning, next generation RDMA systems, and also optical networks.
Okay. Today I'll present our paper titled SRC, a scalable, reliable connection for RDMA with decoupled QPs and connections. RDMA has become the cornerstone of modern data center network. Okay. Due to the performance benefits, the high throughput, low latency, and low CPU overhead provided by the hardware overload transport to the RNIC. It has been widely adopted in the current applications, including the online transition processing, in-memory key value stores, distributed file systems, and the distributed machine learning. The RNIC state size can be gigabyte scales. Each QP consumes hundreds of bytes, plus other states like the memory range states and the transport states. However, the RNIC only have several megabytes of on-chip SRAM using the current technology, which is far less than the total state size. So the RNIC will store states in the host memory and use the on-chip SRAM as a cache. But as the number of QP increases, the limited cache capacity leads to a frequent cache miss. When a cache miss happens, the RNIC must feature the required state from the host DRAM over PCIe, which has much higher latency than the on-chip SRAM. The actual latency and bandwidth contention will lead to a significant performance degradation. Recent studies use the most advanced RNIC will reveal the same phenomena. When the number of connections go beyond a few hundreds, the performance will drop. And in practice, applications require a large number of QPs, so it is very important to address the RNIC scalability issue. The reliable connection, or RC, is the most desired and widely used RDMA transport mode because it guarantees reliable and in-order delivery and supports a full set of RDMA operations. But RC requires a lot of connections. To fully exploit the RDMA's performance, applications often maintain a large number of concurrent connections, which in turn require substantial on-NIC states. Host will communicate with RNIC through QP pairs or QPs, and in RC, the communication is established by connecting a pair of QPs between two nodes. But QPs are separately owned by a different process on the same node, so we need one pair of QPs for every pair of process to support the full mesh communication. Assume a cluster with n nodes. Each node will running P processing. So then we need P times P and the times n plus minus 1 QPs per node for fully connectivities. To mitigate the RDMA scalability problem, the most effective way is to reduce the number of QP requests. In a full connect clusters, we just mentioned before, the software QP sharing will allow multiple processes to reuse the same QPs by multiplexing in the user space. This will reduce the number of the QPs to P times n minus 1, which is more scalable than RC. However, it introduced extra CPU overheads due to contention and synchronizations. The dynamic connected transport, or DCT, shift the sharing to the hardware. It will dynamically establish and maintain a single reliable QP that connects to multiple remote QP as needed. So this will allow each process to maintain only PQPs. However, when communicating with multiple destinations, one DCPs can only connect to one peer at the same time. The DCP will frequently switch the connections, which will increase the latency and bandwidth efficiency. So applications only maintain a large number of the DCT QP pools, which is slightly more than P to reduce the amortize waiting time. And we find that the scalable issue will come from the tight coupled design of the QP and network connections. Each QP is treated as a pair to host to NIC channel and a network connection. This one-to-one mapping will create a redundancy, and with the valuable on-chip RNIC memory, which is limited RDMA scalability. So we propose the scalable reliable connection (SRC), which decoupled QP and connections. In SRC, we redefine the role of the QPs and connections. Application uses QPs simply as a channel to communicate with RNIC, and the connection are no longer tied to the application, but instead it is established only between the RNICs. With this design, multiple applications can share the same connection, and a single connection application can communicate with multiple peers using the same QP. This reduces the number of required QPs and decrease the overall state stored on the RNIC, and effectively mitigate the scalability problem. And this is the overall comparison. Software-based sharing is a pure software solution, while DCT and SRC require hardware change with minor software modification. Compared with the DCT, SRC will eliminate the need for reset-up connections, thus achieve same latency as RC. Achieving this decoupling will present several design challenges, and we must be carefully to address it. The challenge one is minimizing additional states, because decoupling QP and the connection help reduce the total number of QPs. But we still need actual state to manage end-to-end connectivity and secure RDMA access. To maintain consistent high performance, these states should be small enough to fit into the RNIC's on-chip SRAM. The second challenge is efficient state lookup. The RNIC still need to map to a request from QP to its connection, and also map incoming packets from connection back to the right QP. To support this, we need an efficient system architecture and fast lookup data structure. And the third challenge is efficient and friendly abstractions, because new QP types like SRC and DCT will introduce new programming models. But most existing RDMA applications are built on RC abstraction, so the new design must be efficient to program and require minimum code changes. SRC uses software managing mapping between QP and connections, and the software will select this connection when issue a request. This will eliminate the lookup overhead on the hardware. And SRC supports two operation modes. The first one is the SRC managed mode, which is almost fully competitive with traditional RC. And the second one is the application manager mode, which exposes more control to the application and allow advanced management for optimization. Here is our evaluation. This shows that SRC will significantly reduce RDMA state size from 146 megabytes to 0.19 megabytes for 512 server clusters running RDMA applications. When DCT reduced the state size to 0.0414 megabytes per node, it suffers from performance degradation compared to RC due to the frequent connection switching. In contrast, SRNIC achieved a substantial state reduction, while further improved upon RC by delivering better performance without such overhead. In conclusion, SRC decoupled the QPs and the connections to improve scalability, and SRC provide efficient software and hardware architectures. For example, the software manages mapping between QPs and the connections, and a lightweight mapping scheme for efficient forward between the QPs and the connections on SRNIC. Also, there are two operation modes for either compatibility or capabilities. And thanks for your listens.
Great. Okay, we have time for questions. Go ahead.
Very nice talk. I have one question related to how you schedule the QPs to, choose one QP for connection to send packets in next round. Is this done by the software? Since there are many QPs maps to the same connection, the software choose one QP to send in next several microseconds. Is that
so your question
how
is
it works?
Is the software or hardware to choose the QPs?
Yes.
In our design, it's the software to choose the QPs, and it's also the software to choose the connections that select for that QPs.
So another question is that if the software is responsible for choose the QP, if there are many QPs exist in the same time, will this software QP scheduler be a bottleneck for the whole data path?
That's a good question, because our goal of design is to make it similar to the RC scheme. So I think our design currently is use the software to decide this one, and we need further work on this.
Thank you.
Okay. One question. Okay. My question is that when we have some user QP share the same one NIC QP, is there some cost, some trade-off, such as if one user wiki executing in one physical QP, if it fails, and the other UQP will be influenced by this. So also there are some header blocking issues. Is there how do you consider about it? Yeah.
That's a good question. So you mean how can I pick what's the overhead for mapping the software QP to hardware one? Because we care the most about is the connection part, since we already decouple the QP to the connection. So the software QP choose multiple software QP can use one connection to mapping to hardware QP. So I think the overhead, so the trade-off is already minimized. So maybe we need to include that in the future work.
Okay, I have one last quick question. So you compared us at SRC, right? You motivate work. Also, I noticed that you talk about SRNIC. Also, try to address scalability issue, right? It remember it can scale to almost 10,000 connections. So what's a key? Based on your understanding, what's the key? Difference we have SRNIC, why you do SRC based on on top of that? Or what's the fundamental problem with SRNIC that you still think SRC is needed to solve the scalability, reliable connection problem?
Because like SRNIC is still use the RC mode, I think. Yeah, and we think the RC mode use the coupled connection and the QPs, okay. And this one occupies the most memory size on the RNIC SRAM. So okay. We want to decouple this one, so we can store less state size on the SRAMs, so that we can mitigate the scalability issues.
Okay, thank you.
Okay, we probably don't have time for questions. Yeah, KK can take it offline. All right, let's thank Yiren again.